Welcome everybody. My name is Gergő Kovács. I am a jazz pianist. By profession, I have an MSc in chemistry. The following presentation I have made about what is temperament and why keyboard instruments has to be tempered. The word temperament is coming from two Latin words. Temperatio means right measure, right ratio, while temperamentum means mood or temper. When I speak about keyboard instruments, I mean all instruments where the pitch of a note has to be tuned before we play on it. So not only clavichord, piano and harpsichord belongs here, but also organ, electromechanical instruments and synthesizers. What are musical intervals? In this whole presentation I will speak about intervals. And we all know interval is the distance between two notes. So if I get a keyboard, take C for example, I go a fifth up, then I get G. Also I can go again a fifth up, then I get D. Or all across the keyboard, distance between, for example, A and E is a pure fifth. What does it mean by the language of physics? It means that the interval is the ratio of the two wavelengths. So interval, which is a given number, we can see is wavelength 2 over wavelength 1. Because this is just a number, it doesn't matter if we measure the wavelength in meter or millimeter or inch. Also, by rearranging the equation, we can see that we got wavelength 2 by multiplying wavelength 1 with this given number, which is, for example, the pure fifth is 2 over 3, or we will learn that the major third will be 4 over 5. Let's speak about natural harmonics. Take any note, we can call it a bass note, and we will see the harmonics of this note. Because we have just learned that it doesn't matter in what unit we measure the wavelength, so we can approach the problem, let's give a wavelength of 1 to this note. Natural harmonics appear at twice, 3 times, 4 times the frequency of our bass note, and because frequency is inversely proportional to the wavelength, so the natural harmonics will appear at half, third, fourth of the original wavelength. You will see the picture as an illustration of that. We can easily generate natural harmonics on any string instrument. I will use a bass guitar and play the so-called glass notes to get the harmonics. So how these natural harmonics sounds like? I have dropped down the D string of the bass guitar to C, and it is marked as C0 in the picture and has a wavelength of 1 as agreed. What's the first harmonic appearing half the wavelength? You can hear this is the pure octave, so C1 in the picture. What's the next harmonic? 1/3 of the wavelength. We can hear this is the G1 in the picture, so 1 octave plus a pure fifth. The next we can find out in advance because it will have 1 over 4, and 1 over 4 equals 1 over 2 times 1 over 2. So it should be an octave above the C1. Indeed it is. Here comes the interesting part. What's the fifth harmonic? 1/5 of the wavelength. We can hear this is the E, so 2 octave plus a major third. 1/6 equals 1 over 3 times 1 over 2, so it should be the next G note. An octave above the G1, indeed. Here comes the interesting part. What is the 7th harmonic? 1 over 7 equals B flat, if C0 is 1. 1 over 8 I even don't have to play. This is the next C note because 1 over 8 equals 1 over 2 times 1 over 4. what's the ninth harmonic? We can hear this is the D, so D3 in the picture. The next I also don't have to play because 1 over 10 equals 1 over 2 times 1 over 5, so it should be the next E note. The 11th harmonic, as you can hear, is the F sharp in this third octave. Now we can see that a very nice scale starts to appear in this third octave. It is called the harmonics scale. The 12th harmonic I also don't have to play because this should be the G above, because 1 over 12 equals 1 over 2 times 1 over 6. Here comes the interesting, what is the 13th harmonic? You can hear that this is the A in this third octave. What is the 14th harmonic? It should be the B3, B flat 3, because it should be the 1 octave above 1 over 7. Now, before we go further, you can guess that one is the 16th harmonic. It should be the C4 because it's again an octave above 1 over 8, which is C3. And what's this? The only note which should be between B flat and C, it should be the B. Indeed it is. How interesting it is that in the harmonics, both the B flat and the B appears, so both the minor and the major seventh. Before we go further, I want to emphasize two more things. We can count what is the pure fifth. We discussed that a given interval means, by physics, multiplication of the wavelengths. So we can make it reverse. So if we divide or multiply by the reciprocal, then we get the same step down. So applying this, the pure fifth, which is G0 in the picture, should be an octave below G1. So it means multiplication by 2, which should be 2 over 3. This is our pure fifth. With the same logic, the major third will be 2 octaves below our E2, so it should be multiplying by 2 by 2, so by 4, it's 4 over 5. This is the E0, which is our major third. And we have to remember this, and on the next slides, we will make calculations with this. So let's calculate intervals. Imagine that a piano tuner comes to our house and tune the piano by ear. So he tunes one note with a tuning fork and all the rest by ear as a chain of intervals. What does it mean? Tuning one note from something what has already been tuned. Just to remember, I have written in all these slides that an octave step up means multiplication of the wavelength by 1 over 2, and an octave step down means multiplication by 2. Also, a pure fifth means multiplying the wavelength by 2 over 3, and the pure fifth down means dividing by 2 over 3 or multiplying by 3 over 2. Also, a major third means multiplying 4 over 5 up and down. It means multiplying 5 over 4. So let's calculate our E from our base note C. Why we have to calculate this? We have just learned that the major third is 4 over 5. Okay, but let's do it like a string instrument, so tuning pure fifths. So from C we get the G, which is a pure fifth, so this is 2/3, and from G we have again a pure fifth to D, and then again to E and to E. So this means mathematically 2/3 times 2/3 times 2/3 times 2/3. This is the E, and then we have to go down 2 octaves, so times 2 times 2. what we get is 64 over 81, or in decimals 0.790. How this number is in relation with the pure harmonics E0, what we learned, this is 4 over 5, or for comparison, this is 64 over 80, or in decimals 0.8. Now we are in trouble because we see that these two E notes are different. And how it is different? The number is smaller, so the wavelength is smaller, means the frequency is bigger than the pure harmonics E. So this E note will be slightly sharper than the pure major third. Okay, what is A calculating from C? This is easy. We go 3/5 up, so GDA, and then we have to go down 1 octave, so this is 2/3 times 2/3 times 2/3 times 2, which is 16 over 27, or in decimals 0.592. Yes, but everybody who has learned music knows that A is the third in F major. So let's count like that. So F is going down a pure fifth, so this is 3 over 2, and we have to go up an octave, so times 1 over 2, and then we have to go up a major third times 4 over 5. What we get is 3 over 5, or 15 over 25, or 0.6 in decimals. Yes, but remember, A appeared in the harmonics, and it was which harmonic? The 13th. So bringing this down to the octave we are working, you will get 8 over 13, which is 0.615 in decimals. Now we are in real trouble because we get 3 different A notes by 3 different methods. And here I want to remark, if you hear a folk singer singing a pure A as a harmonic, maybe you will hear it flat and out of tune, but maybe he has right and not you. Also, I want to emphasize that having 12 notes in an octave is a matter of choice. Now you can see, so if you speak to an Indian sitar artist, he will easily play these 3 different A notes as 3 different notes, and he will not understand that why we want to make one out of these 3 notes. Okay, let's go further and calculate B flat from our base note C. This is again easy. We go down pure fifth, so to get from C, F, and then B flat, and then we have to go up 2 octaves. So this is 3 over 2 times 3 over 2 times 1 over 2 times 1 over 2. What we get is 9 over 16, or in decimals 0.562. Yes, but remember, B flat appeared in the harmonics being the 7th harmonic. So bringing it down to this octave, we got 4 over 7, which is in decimals 0.571. Again, very different. Okay, go further, be brave. Let's calculate F sharp from our base note C. This is easy. F sharp is the third in D major. So what is D? D is going 2/5 up, then bringing down an octave, and then again a major third up, then we get F sharp. So 2/3 times 2/3, down an octave times 2, up a major third times 4 over 5. What we get is 32 over 45, or in decimals 0.711. Yes, but remember, F sharp appeared in the harmonics, and this was the 11th harmonic. So bringing it down to this octave, we will get 8 over 11, or 32 over 44. Close, but this is not the same. And in decimals, this is 0.727. Might be the problem with our pure fifth, then let's use only major thirds. So calculate G sharp, which is the third in E major, from our base note C. This is easy. E is 4 over 5, we just learned, and going up another major third, we get G sharp, which is 16 over 25, or in decimals 0.64. Okay, G sharp is an harmonic to A flat, and from A flat we have also a major third until the next C note C1. Is it true? To get the result, let's divide the two wavelengths, because then we got the interval. So let's divide 1 over 2 with this 16 over 25, which means we have to multiply by 25 over 16. The resulting number is 25 over 32, which is in decimals 0.781. This is far from the major third, which is 0.8. I can even say this is almost closer to the pure fourth, which is 0.75. So the GC relation. Or an alternative approach, let's add 3 major thirds, one the above, and then we should get a pure octave. So what you get is 4 over 5 times 4 over 5 times 4 over 5. This is 64 over 125, which will never be 0.5, which is the pure octave. The resulting C1 will be flatter than the pure octave. What's the consequence of the previous slides? Maybe the math doesn't work? No, it works. But we have to make choices. We can tune pure intervals by ear in one key, in our case C major. This will result in a tuning which is very nice in that key, but useless in every other key. Or we try to create a system where the intervals are slightly detuned, but we can play in every key. How to do this? We have to tune the fifths a little bit narrow, so slightly lower the pitch. And we have to tune the major thirds slightly wide, so higher in pitch. And exactly this is called temperament. There are different temperament systems from which I will examine only 2 in the coming slides. First, I want to speak about equal temperament. Equal temperament is used since the 19th century till nowadays, so we hear it on radio, on YouTube, and basically our ears are used to that one. Equal temperament means that the difference from pure intervals are spread equally between the 12 notes. Or, in other words, every minus second is the same. As a consequence, in equal temperament, all keys will have the same color. We can easily calculate what is this minus second, this x, which is multiplied 12 times, will give a pure octave, which is half. So x under 12 equals half. We take the logarithm, so 12 times log x equals log half, so the x will be 0.94387. This is a minus second, and with this minus second we can build up our pure fifth and our major third as our 2 most important intervals. And remember, I have said that the pure fifth always has to be tuned narrow, so slightly lower in pitch, and the major third always has to be tuned wide, so slightly higher in pitch. So what we get is the major third is a smaller number, so higher in pitch, and the pure fifth is a higher number, the wavelength, so the pitch is lower. Perfect, it works. The other temperament I want to speak about is the so-called Werckmeister temperament. It was invented by Andreas Werckmeister, who himself was an organist, an organ builder, a composer, and also an astronomist. He published his book Musikalische Temperatur in 1691, and this system was used in the 18th century, so it was used by Buxtehude, then Bach, and all other Baroque composers. The idea here is that C major on the top of the circle of fifths is tuned the purest. It is not tuned pure, but it is the purest of all keys. And as we go down in the circle, we arrive to F sharp major, which is the less pure harmony. So in other words, it is the most out of tune, but it is not out of tune to an extent that you cannot play with that. And exactly this is the idea in the Werckmeister temperament, that different keys has different colors. So you do not need perfect pitch to recognize the keys. Let's listen to these temperaments. If we tune a major chord pure, then the resulting tone will have no change over time. It will be still. But if we tune it a little bit out of tune, because we want temperament, then a vibrato-like effect, a wobbliness will appear, like wow, 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 wow. And what we have to listen here is exactly the speed of this wobbliness. In equal temperament, all major chords has the same speed, like 5 to 6 per second. Do you hear? Wow, 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 wow. Okay, this is what we are used to. Let's listen to the Werckmeister, where the speed will be much slower, like 2 to 3 times per second. This is much nicer, much calmer. I want to remark that I play these harmonies in the octave which is below the middle C on the piano, because these nuances, these little differences, are best heard in that region. So as a consequence, the next chord, the G major, I will play as D, G, B. So the third will be on the top of the chord, and the difference will be even more noticeable. This is G major in equal temperament. Then listen the B on the top of the chord at the Werckmeister. This is singing much nicer. I will not show all the chords, but some of them. The next will be the A major, A major in equal temperament, 5 to 6 times a second. Wow, 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 wow. Werckmeister temperament, it will be similar speed, but the color will be absolutely different, much more dramatic A major. As I said, in the Werckmeister temperament, on the top of the circle of fifths, the harmonies are more pure than the equal temperament. We have to give it back somewhere, which is on the bottom part of the circle of fifths. So let's listen to F sharp major. This is F sharp major in equal temperament as we used to hear. Okay, then Werckmeister temperament F sharp major will be much more hectic, much more out of tune, much more interesting in the other hand. I also want to show to you the E flat major, and please listen to again the third in the middle of the chord, this G, whether it is singing or not, or how it is singing. Werckmeister counterpart. Hopefully you also hear that the G in the middle of the chord is a little bit, how to say, outstanding. It's a little bit like alien, okay? And lastly, I want to again show the F major close to the C. This is F major in equal temperament, and again, please also listen to this A note, the third, how it is singing or how it is not singing. The same in the 18th century. Again, much nicer, much calmer. As a summary, I want to emphasize 3 things as a message what you can bring home from this presentation. First, we learned that all piano and all other keyboard instruments which are tempered are by definition out of tune. So, dear teachers, dear choir leaders, do not try to teach intonation to a choir on the piano. It won't work. Please try to sing where the notes has to be, and then the students can learn. The second thing I want to emphasize is that if I get a violin or viola or cello, which are by definition pure because the player decides where are the pitch of the notes, for these instruments it is very difficult to play together with the tempered instruments like a piano. So I really admire all the classical musician colleagues who are playing in a violin, cello, piano, trio sonata, because there the violinist and the cellist has really hard task to do. And third, please be brave to use this Werckmeister temperament not only for Baroque music, but also Mozart, Beethoven, and even Chopin. I am lucky because in my digital piano I can change the tuning system with only one button, and I want to say that nowadays even the jazz I play in Werckmeister temperament. Why it is important? Because as we discussed, different keys has different colors. So all of a sudden you will start to understand why a Chopin waltz is written in C sharp minor, or why a certain Beethoven piece is written in A flat major. It has a reason, because these key colors are different. Thanks for watching. If you like this video, hit subscribe.